Hi, here's an interesting problem with many variations depending on what you choose to be the highest number in the starting set. So in this problem, I'll use 14. And the problem is divide up the numbers between 1 and 14 into two disjoint sets so that the product of the numbers in one set is equal to the sum of the numbers in the other set. For example, we could try 13 and 14 in one set and the numbers 1 to 12 in the other set. But 13 times 14 is 168, and the sum of the numbers 1 to 12 is 78. And these are not equal, so this division does not work. So to solve this problem, the first thing we're going to note is that the sum of the numbers from 1 to 14 is 105. This problem is then equivalent to creating one subset of the numbers from 1 to 14. We'll call this set A, such that the sum of the numbers in this set, we'll call this S of A, plus the product of those numbers, we'll call that P of A, is equal to 105. So S of A plus P of A equals 105. And I'll let you figure out why this is true, why this is an equivalent problem. So we're going to start by putting an upper limit on how many numbers we can put into the set A. So the first thing we note is that 5 factorial is greater than 105. So this means A can have a maximum of 4 elements in it, or the product would already be too big. And obviously a minimum of 2 elements, since there's no 1 element set for this will work. That should be obvious. So we'll call the number of elements in set A n, and then we will then check n equals 2, n equals 3, and n equals 4 as 3 separate cases. Case 1, n equals 2. So we'll let the set A equal A and B, with A strictly greater than B. Note, they can't be equal since each element has to be a different number from 1 to 14. So then we have S of A plus P of A is equal to A plus B plus A times B. And all this, of course, is equal to 105. So we're going to do a nice little trick here. We're going to add 1 to both sides. And this allows us to factor the left-hand side. So we have AB plus A plus B plus 1 equals 106. And factoring gives us A plus 1 times B plus 1 equals, and then factoring 106, 53 times 2. And we'll want to factor the right-hand side eventually, so I just did it directly. And what we notice is that this requires A or B to be 52. And that's too large, since the largest number is 14. So we see immediately there are no solutions for n equals 2. So we're done with case 1. So we'll look at case 2 when n equals 3. Now our set has 3 elements, A, B, and C. We can say that A is strictly greater than B, which is strictly greater than C. So now we have S of A plus P of A equals A plus B plus C plus ABC equals 105. So the next step is to find a maximum possible value for the smallest element, C. And we notice that 4 times 5 times 6 is already bigger than 105. So C can't be 4. C must be strictly less than 4. So we're going to check the 3 subcases, C equals 1, C equals 2, and C equals 3. And we'll check each one separately. But first, to make the checking easier, we're going to do a little algebra manipulation. So we'll multiply our equation by C. And this will give us AC plus BC plus C squared plus ABC squared equals 105 times C. We then rearrange the terms and add 1 to each side, which gives us ABC squared plus AC plus BC plus 1 equals 105C minus C squared plus 1. The reason we've done this is we can now factor the left-hand side. So the left-hand side becomes AC plus 1 times BC plus 1. And to make things a little bit easier, we're now going to call the whole right-hand side K. And K in this case equals, of course, 105C minus C squared plus 1. And our equation is now AC plus 1 times BC plus 1 equals K. Now note that since A is bigger than B, AC plus 1 is bigger than BC plus 1. And so what this means is that AC plus 1 has to be bigger than the square root of K. So this gives us a lower bound on one of the factors here. And we also know that A has to be less than or equal to 14, since that's the biggest number in our set. So this means that AC plus 1 must be less than or equal to 14C plus 1. So this gives us a bounded expression for AC plus 1, one of the factors on the left-hand side. And AC plus 1 has to be between the square root of K and 14C plus 1. And it cannot be equal to the square root of K, but it can be equal to 14C plus 1. So now for each value of C, we have a strict bound on A, and we just have to factor K. So look at subcase 1 when C equals 1. In this case, K equals 105, which equals 3 times 5 times 7. And the square root of K is bigger than 10. So what we're going to do is we're just going to say that the square root of K is bigger than the integer value of the square root. We don't care about the decimal value. We only care about that it's bigger than some integer value. Because everything we're dealing with is integers. And 14C plus 1 equals 15 in this case. So this means that A plus 1 has to be between 10 and 15. So if we looked at our equation now, we have A plus 1 times B plus 1 equals 3 times 5 times 7, where A plus 1 has to be between 10 and 15. This only gives us one option, and that's A plus 1 equals 3 times 5, which is 15, which gives us A is 14, B is 6, and we have a solution where the set A is 1, 6, and 14. And that's the only solution for n equals 3 and C equals 1. Subcase 2, where C equals 2. Now K is equal to 207, which is 3 times 3 times 23. And K, square root of K, is greater than 14. And 14C plus 1, and C is 2, is 29. So now our bounds on our expression, which is 2A plus 1, remember it's CA plus 1. So our expression on 2A plus 1 is between 14 and 29. So our equation is now 2A plus 1 times 2B plus 1 equals K, which is 3 times 3 times 23. And the biggest factor, 2A plus 1, has to be between 14 and 29. And the only option that fits these constraints is that 2A plus 1 equals 23, which gives us A equals 11 and B equals 4. So we have one more solution now for n equals 3 and C equals 2, and that solution is the set A is 2, 4, and 11. Subcase 3, C equals 3. I'll let you go through the details, but a similar type of check for C equals 3 will show there are no solutions since K will equal 307, which is a prime number, and so there'll be no values in range. So now we take case 3 when n equals 4. And here we'll let our set equal A, B, C, D. Again, with A strictly bigger than B, strictly bigger than C, strictly bigger than D. We then have S of A plus P of A equals A plus B plus C plus D plus A, B, C, D equals 105. And as we did earlier, we're going to set an upper limit on the smallest element, D. And here we can note directly that 2 times 3 times 4 times 5 is bigger than 105. And so that makes it easy. D has to be 1. So then we rewrite our problem with D as 1. So now we have S of A plus P of A equals A plus B plus C plus 1 plus ABC equals 105, which is equivalent to A plus B plus C plus ABC equals 104. And now this is exactly the same as case 2, except the equation is equal to 104 instead of 105. But we can use all the same methods. And by a similar argument as in the last case, we know that C must be 2 or 3. C can't be 1 because D equals 1 and all the numbers are distinct. So we're going to have two subcases to check. I won't go through all the details of the cases here, but I will list the critical values in a table for you to check yourself if you like. But the process is the same as before. However, note that now k is equal to 104c minus c squared plus 1. So here are the critical values for c equals 2 and c equals 3. We have k is 205, which is 4 times 41. And for c equals 3, k is 304, which is 2 to the 4th times 19. For c equals 2, the square root of k is bigger than 14, and for c equals 3, the square root of k is bigger than 17. 14c plus 1 is equal to 29 for c equals 2, and 43 for c equals 3. So for c equals 2, ac plus 1, we don't get any numbers in range. And for c equals 3, for ac plus 1, we do get 19 will give us an a in range. And that'll give us our final solution, where the set A equals 1, 3, 5, 6. So now we found all three ways to partition the numbers 1 to 14 into two distinct sets, such that the product of the numbers in one set is equal to the sum of the numbers in the other set, and there are no other solutions besides these three. Thank you.